So this just says inertia of a disk. So I'm going to solve through a couple different ways of getting the moment of inertia for a disk. So the most common would be the moment of inertia about an axis which goes through its center and is perpendicular to the disk. So the moment of inertia for a solid mass object is going to be the integral of r squared dm. And so the trick here is identifying your dm. So what we do in the disk case is identify some small area. We need to have our mass defined. And so if our mass is its density times its area, where in the case of a disk, that would be rho times pi r squared, where r is its outer radius. Then we can identify a small mass term at some radius r having some thickness dr, and we can visualize this by extending out. So essentially taking this circle, pulling it out, and then cutting it and laying it flat. And so it would have some radius or some thickness dr, and its length, because it's a circle, would be 2 pi r. And so then its area would be, so a small area would be 2 pi r dr, and its mass would be rho dA, which is just rho times 2 pi r dr. And so then there are our small units of mass, right? And so then now we have everything in place to plug into our mode of inertia equation. So r squared dm, which is then integral r squared rho 2 pi r dr from 0 to r. And we can bring out the constant terms, so 2 pi rho, and then integral from 0 to r cubed dr. So the integral of r cubed, with a power, you always put up the power by 1 and divide by the value. So then it's 2 pi rho r to the 4th over 4 from 0 to r. And then when it's 0, it's going to be completely 0, so we just really need the top solution. So 2 pi rho r to the 4th over 4, or pi rho r to the 4th over 2. And then we can make one more simplification here. So our mass, we said, was rho pi r squared. If we look over here, we have a rho, a pi, and an r to the 4th. So we can take these terms out and say that this is our mass, r to the squared over 2. Okay, so it's just mr squared over 2. So that's simple. But moment of inertia depends on your axis system choice. So if we say swap the axis and instead use that one, which goes through its center, even though it doesn't look like it does. I'm just going to redraw that so that it doesn't look like I'm trying to do something crazy. And I don't know if that was any better, but all right. We're going to do an axis that's perpendicular or that lies in the plane of the disk and goes through its center. So again, here the trick is identifying your small mass segment. And so remember that we're dealing with perpendicular R's. So now the small mass segment has to be a straight line. And now I'm just going to expand that a bit. And so if we look at just the half of the circle, then our R's are going to go from, are just going to be these lines, and we need to sum them all up. Another way of representing it, though, is by theta. And that turns out to actually be the easier way to solve this. And so that's our R. If we define some theta, then if we look, these hypotenuses here are radii. And so this here is R cos theta, which means that this length, this line segment that I have here, which would have a radius of dr, or a thickness of dr, sorry. The length of it is going to be 2r cos theta. But what's dr? Well, if we look, r is r sine theta. And we can actually define dr through differentiation here. So dr is then r cos theta d theta. And now our area segment, which as we defined previously, but our area segment now is just the length times the width, which is going to be 2r squared. I'll just write it all out, actually. So 2r cos theta times dr, but dr is this. So r cos theta d theta, which is then 2r squared cos squared theta d theta. And so that's our area segment. And so our mass, just as previous, is going to be rho times our area segment, which is then 2 rho r squared cos squared theta d theta. And now our moment of inertia is integral r squared dm. We're going to use this definition of r. So integral r squared sine squared theta times our dm, which is 2 rho r squared cos squared theta d theta. And we're going to integrate from 0 to pi over 2, because I already included both sides of the semicircle here. So we just need to go up to pi over 2, so just a quarter of the circle, and that encompasses both sides of the half. But now if we look, I'm only doing half of the disk. So to get the other half of the disk, we just need to multiply this by 2. So our moment of inertia is going to be 2 times this integral from 0 to pi over 2 of all these terms. And now pulling out all of our constants, and in this case our capital R is our constants. So we've got 4 rho r to the 4th integral 0 to pi over 2 sine squared theta cos squared theta d theta. Now this guy is not something that I know how to solve right offhand, so I just used an integrator. I looked it up online to get the indefinite integral. And so this comes out to 1 over 32 times 4 theta minus sine of 4 theta from 0 to pi over 2. And now we can do this all out fully, but if we look, right, if we put a pi over 2 in here, then this actually has a value. So 1 over 32 times 4 times pi over 2. Now if we plug in a pi over 2 into sine of 4 pi, well, that's sine of 2 pi. Sine of 2 pi is 0, so that goes to 0. And then if we plug in a 0 into either of these values, that's 0. So this is the only term that survives. And so just for simplification, I'm just going to use that term. I said that, but now I'm thinking might as well just do it. So I'm just going to do sine of 4 times pi over 2. And then minus 1 over 32. 4 times 0 minus sine of 4 times 0. So just to write it out, so this is sine of 4 times pi over 2, which is sine of 2 pi, which is 0. That's 0. And sine of 0 is 0. So those terms all go to 0. Okay, so then all we're left with is this term. So we can pull the 4 out, or, well, I guess we're just multiplying everything together anyway. So 4 times 4 is 16. Rho, r to the 4th, and we've got a pi. And then we're dividing by 32 times 2, which is 64. 16 over 64 is 1 over 4. So that's rho r to the 4th pi over 4. And if we remember, our mass is rho pi r squared. So then this is just mr squared over 4. And so then there's our moment of inertia for a disk rotating about an axis which lies in the plane of the disk and goes through its center. So it's different because it depends on which axis you choose. And it takes a bit more work than the other kind, but not too much. Okay, so there's our two of the moments of inertia. Obviously, you could define an almost infinite array of axes, but there's a couple of the most common ones. If we look at the solution given here, we have the most common one, which is the axis which is perpendicular, so a half mr squared. So I would say that's still correct. So the moment of inertia for axis in the plane is mr squared over 4. Others are possible. And they can actually be derived from those as well. But that's for a different lesson.